Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. Today we're going to continue our discussion of probability and talk about the difference between independent and dependent events, and also talk about how to find the probabilities of both. So to get us started, we have 6 little scenarios here, and we're going to try to sort these into 2 different categories. And there may be 3 in one category, 3 in another, there may be 1 in one category, 5 in another. Pause the video though, take some time and see if you can spot the similarities and differences between these scenarios and find the 2 groups that they should go in. Okay, so, and there could be some arguments for different answers here. I mean, we're going to think about this from a probability perspective rather than any other sort of categorization. So we have flipping a coin twice, drawing 1 card from a deck and then drawing a second without replacing the first, shooting 2 free throws, rolling a die and then rolling it again, winning the lottery and then buying a yacht, and being born in Las Vegas and becoming a Knights fan. So how I would separate these, I would put flipping a coin twice, shooting 2 free throws, and rolling a die and then rolling it again, I would put those in the same category. And I would put numbers 2, 5, and 6 in a different category. And the reason I do this is because the ones I circled in red, well, the second occurrence or the second thing that's happening, right, in number 1, the second flip of the coin, is unaffected by the first flip. For number 3, the second free throw is unaffected by the first. Now, you could make an argument in a basketball game if someone, is in a high pressure situation and, they miss the first, maybe there's more pressure on them to make the second, or they're more relaxed if they make the first. But if you just have a, professional basketball player, for all intensive purposes, right, the probability of them making a free throw is going to stay pretty consistent, regardless of how they do on their previous free throws. And number 4, the second roll of the die is going to be unaffected by the first roll, right? I'm no more likely or less likely to roll a 6 or a 5, regardless of, or depending on whatever I rolled the first time. Now, 2, 5, and 6 are kind of the opposite, right? If you draw 1 card from a deck, don't put it back, and then draw another card, well, there's going to be no way you can draw that first card again, right? Let's say you draw the ace of spades, you put it off to the side and you draw another card. Well, we know that that second draw from the deck is not going to be the ace of spades. And because there's 1 less card removed, or 1 less card in the deck, there's actually a higher probability that you draw, let's say, the jack of hearts. Right? The first time, let's say you want to draw the jack of hearts. Well, the first time you've got a 1 out of 52 chance, right, for the jack of hearts. There's 1 jack of hearts, there's 52 cards. Well, the second time, after the ace of spades is removed, you have a 1 out of 51 chance. Because there's still 1 jack of hearts, but there's one fewer card in the deck. So the probability of the second draw is affected by the probability of the first, or by what happened during the first draw. Same thing with 6. People generally, I know it's not a hard rule, but generally, most sports fans are centered around the team that they live near, right? So if you're born in Las Vegas, you're probably more likely to be a Knights fan than if you were born in Philadelphia, right? I know it's not always true, but generally it's true. So becoming a Knights fan is many times dependent on whether you were born in Las Vegas or born somewhere else. Okay, let's look at another scenario here, sort of like the yacht example, but now we're going to actually get into some probabilities. So it says John plays the lottery every day. His chances of winning are 0.0001, right? Very, very small. If he wins, then the probability he buys a new car is 0.9999. So very, very large. Well, the question is, do you think John is likely to get a new car? Why or why not? So pause the video, write down your thoughts. Is it likely John gets a new car? Well, if we just looked at the second sentence here, right, if we just looked at the probability he buys a new car is 0.9999, we would say, yes, it is likely, But that's dependent on whether he wins the lottery, which is the probability is very, very small. So the answer here is no, right? The answer is that he's very unlikely to get a new car because he would have to win the lottery first, right? If he wins the lottery, he's basically guaranteed to buy a new car. But the problem is he's not going to win the lottery very often, so that it doesn't really matter what the chances of him buying a car are because he's got to get through the lottery first. So we would say no, because buying a car is dependent on winning the lottery, which is unlikely. And we're not going to quite calculate what the actual probability is here. We will do that later in the lesson. We can just kind of tell that it's small, based on the fact that winning the lottery is a very small probability for John. Before we get into dependent events, though, because they're a bit more complicated, we are going to start with independent events. So let's look down here. Independent events, events where one event does not affect the probability of the other. And we looked at some examples of independent events up above, right? Flipping a coin twice, shooting 2 free throws, rolling a die, and you could for certain come up with an infinite number of other independent events. The probability, though, for figuring out the likelihood of both occurring is right here. The probability of A and B, and again, this is when they are independent, is going to be the probability of the first event occurring times the probability of the second event occurring. So let's do probably the most basic example, getting heads on 2 coin flips. So I want a heads on my first flip, and I want a heads on my second flip. So our first event, we'll call that A. Event A, heads. Event B is also going to be heads. So the probability of A and B occurring, well, the probability of A, bunch of oopses right here. Probability of A and B is going to be equal to, well, the probability of getting heads on a coin flip is 0.5 or 1 over 2. Right, there's one side that's heads, there's 2 sides total, so 1/2. Probability of heads occurring on the second flip, well, that's also 1 out of 2. So the probability of heads on both flips is going to be 1 out of 4. You could also say 0.25. Either one is acceptable. So you just need to find the probability of both events occurring and then multiply them together. And this is when one event does not affect the other. These are independent events. Let's look at one more example, but we'll have you guys practice before you come back and check the answers. Little spinner problem. These are fairly common with basic probability when you're learning. It says, given the spinner below, find the probability of the following. And you have 3 different scenarios. So pause video, see if you can come up with these probabilities. Do not round. So if you want to write it as a decimal, it needs to be an exact decimal. Otherwise, leave it as a fraction. Okay, so first probability we need to find is landing on a 3 and then a 2. Well, this is a pretty basic spinner. There's 6 spots on the spinner. They're all the same area, so they're all just as likely to occur as any of the other ones. If I want to land on a 3, so let me just write this out. The probability of 3, then 2, is going to be equal to, well, 1 out of 6. That's the probability of landing on a 3. Times probability of landing on a 2. Well, that's also 1 out of 6. So we get 1 out of 36 as our probability for both of those happening. Okay, on to part B. It says landing on an odd number and then on a number greater than 3. And we'll switch up the way we write this just so you see it differently. We'll call this event A. We'll call this event B. So that way I'll just write probability of A and B. Well, the probability of landing on an odd number, there are 3 odd numbers here, 1, 3, and 5. So that's going to be, you can either write it as 3 out of 6, or you can write it as 1 out of 2. If you write it as 1 over 2 or 1 out of 2, it's going to save you some simplifying at the end. The probability of it landing on a number greater than 3, well, that's also 3 out of 6, right? Because 4, 5, and 6 are greater than 3. So if I multiply those together, I get 9 out of 36, which ends up being 1 out of 4. So the probability of those two things happening back to back is 1 out of 4. This one could also write as 0.25. On to our last one. First event is landing on a 1. We'll call that event A. Second event is landing on a factor of 4. So you can see they're testing, some different math skills in these probability problems. If you don't know what a factor is, you're not going to be able to, or it's going to be unlikely to get this problem correct. The probability of landing on a 1, well, that's going to be 1 out of 6. Probability of landing on a factor of 4, well, if we think about the factors of 4, we have 1, 2, and 4. So that's going to be 3 out of 6, or we could write 1/2. So we get 3 out of 36, which is equal to 1 out of 12. And that finishes our problem dealing with independent events. Let's now move on to what dependent events are, how to find them, and then we'll do an example or two. All right, so dependent events. This is where one event does affect the probability of the other. So it was like in our lottery example, right? Buying a car was dependent on being able to win the lottery. And the way we find this, this notation looks a little different. It says if A and B are dependent events, then the probability of A and B is going to be, well, the probability of A times the probability of B given that A has occurred. That's what this notation means right here. And you want to be familiar with that, right? If you see probability of B with that vertical segment there, B/A, well, that reads the probability of B given that A occurred, right? Because if A didn't occur, then, well, the probability is 0, right? If we are only going to buy a new car, given we win the lottery, and we don't win the lottery, well, it doesn't matter, right? We're not going to get that new car regardless of how high that second probability is. So let's go through an example here. I'd actually like to go back up to our lottery example first, because I did say we were going to figure out what the actual probability was here. So based off of that formula, can we apply it to these two probabilities to find the probability that John is likely to get a new car? And we are going to assume that John is not going to buy a car if he doesn't win the lottery. right? Maybe you may argue, well, he may buy a new car anyway. No, he's only going to buy it if he wins that lottery. So pause the video, see if you can come up with that probability. Well, chances of winning the lottery, that's going to represent the probability of A. Probability he buys a new car, that's going to represent the probability of B. That's our second event in this dependent scenario. So the probability of A and B, these are dependent events, is going to be equal to 0.0001 times 0.9999. And if we multiply those together, we end up getting a very, very, very small number. This turns out to be 0.0000999. And maybe we don't really understand how small this number is, but let's think about it. If we have a probability of 1.0, well, that's going to be every time, right? That means that the event is always going to happen 100% of the time. If we have a probability of 0.1, well, all of a sudden we're dividing that percent by 10. So it's going to happen 10% of the time, or 1 out of 10. And if we keep following this pattern, 0.01, that's about 1% of the time, or 1 out of 100. If we go to 0.001, that's going to be 0.1%, or 1 out of 1,000. And this next one is actually the closest to our purple probability up here, 0.0001. That is approximately 0.01%, or 1 out of 10,000. Right? If you rounded this 0.0009 up to 0.0001, it's really very, very close. This is very, very close to this number, so we'll just assume that it's the same for all intents and purposes. There's about a 1 out of 10,000 chance, right, that John gets a new car. Even though he's almost guaranteed to get it if he wins the lottery, winning the lottery is very, 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 very small as far as probability goes. Okay, let's do one more example for dependent events. So there are 2 lemons and 1 lime in a bag. Kyle takes 1 piece of fruit out of the bag and then takes another piece of fruit out without replacing the first. And this is actually key. This with and without replacement, right? If you replace something and then draw again, like if you take a card from a deck, you replace it and then you draw again, well, that's going to be an independent event, right? Because the deck is set up the same exact way the second time you draw from it as it is the first. And it's the same thing in this example, right? If you took a piece of fruit out of the bag, but then you put it back before you drew again, well, these would all of a sudden be independent events because the second time you take a piece of fruit, you have the same options, the same probabilities as you did when you withdrew it the first time. But when you don't replace it, all of a sudden it makes it a dependent event type of scenario. So take a look at these 4 different questions, find the probabilities using the dependent events formula, and then come back and see how you did. Okay, so for the first one, we have take out a lemon followed by taking out another lemon. Well, the probability of taking out a lemon is 2 out of 3, right? There are 2 lemons to start with and 1 lime. Now, if you take out a lemon and you don't replace it, well, there's 1 lemon left and there are 2 pieces of fruit. So the probability of taking out a lemon for the second draw is 1 out of 2. And if you multiply these together, you get 2 out of 6, which is equal to 1 out of 3. So you have a 1 in 3 chance of drawing 2 lemons without replacement. Second one, taking out a lemon followed by a lime. Well, we know the probability of taking out a lemon on our first draw is 2 out of 3. Taking out a lime on our second draw, well, there's 1 lime, and then there's only 2 pieces of fruit left the second time, so 1 out of 2. This also gives us 2 out of 6, or 1 out of 3. Taking out a lime followed by a lemon, well, if you want to draw a lime first, there's only 1 of them, and there's 3 pieces of fruit. If you get that lime, you don't replace it, well, there's 2 lemons left, and there's only 2 pieces of fruit. So you're guaranteed to draw the lemon, 2 out of 2, or 1 out of 1, or 1. This ends up giving us also 2 out of 6, or 1 out of 3. Now you may be thinking, well, this part D is going to be 1 out of 3 too. It seems like it's the key number here. Well, let's think about it. Part D is taking out a lime followed by a lime. Well, the probability of drawing a lime on the first go around is 1 out of 3. But if you don't replace the lime, all of a sudden there's 0 limes and 2 pieces of fruit. So 0 out of 2 is the probability, or just 0, of drawing a lime the second time. That means that your probability of drawing 2 limes is equal to 0. And that makes sense because there's only 1 lime in the bag and you're not replacing it if you draw it the first time. Okay, that's going to do it for this lesson on independent and dependent events. We'll get some more practice in during class, but until then, enjoy the rest of your day, and we'll look forward to seeing you next time.